In this video, we're going to look at a question from Engineering Dynamics Learning Outcome 2 tutorial sheet. This is on page 7 and it's question number 3. This question asks us to do some calculations involving angular motion, and you'll see in part C we're asked to do a velocity time diagram in order to determine the number of revolutions of this motor in the period of motion described. So what we'll do is we'll tackle this question in the way we usually do. We'll look for all the information in the question, we'll break it down accurately, and we'll solve it step by step, making sure we don't skip out any important details. The first thing to notice is the question tells us the motor started in 2 stages. And this should be a clue to us that we're going to have 2 separate sets of calculations. We're going to have the motion in the first stage and then the motion in the second stage. So it can be helpful to write down these headings, stage 1 and stage 2, to separate out the information we're given in the question. We're told in the next sentence that it is accelerated from rest and runs to an intermediate speed of 3000 RPM in 6 seconds. So we're given a time and we're given angular velocity. We're given a starting velocity and we're given a final velocity for this stage. So we can write down these pieces of information. We know that omega-1, our initial velocity, is going to equal to 0. Now when something's 0, we can choose which units are going to enter, because 0 radians per second and 0 RPM are both 0. So we can say this is in radians per second already. These are the units that we need to use for this question. And then we have omega-2, and we're told this is 3000 RPM. And we know straight away that we will have to convert this. And the way we can convert RPM is by multiplying by 2 pi and dividing by 60. And multiplying by 2 pi converts revolutions into radians, and dividing by 60 changes it from per minute to per second. And we've got a formula for doing that on page 6 of the course notes, but we can also recognise this multiplication here, times 2 pi divided by 60, is what's required to convert from RPM into radians per second. And if we do this calculation, we're going to see that this is the same thing as 100 times pi. And there's nothing wrong with writing down 314.12 and whatever else comes after that with pi, but leaving it as 100 times pi means this is an exact value for our calculation. This is 100 pi radians per second. Makes you more comfortable though. You can stick that into your calculator, and what you'll see is 314.1592654, and of course pi being infinitely long number, it would continue like that. So if you prefer 314.159, say, write that down. I'll write it in brackets here. And we also know the time. The time is given to us as 6 seconds. So we know before we write down anything else, we have enough information here to start doing some calculations. Can we have 3 pieces of information about motion? Then we can do some calculations with it using our equations of angular motion. But let's finish gathering information from the question before we start solving any problems. We're told the motor starting mechanism then accelerates the motor at a rate of 40 radians per second to a top speed of 4000 RPM. So in the second stage of the motion, we know a few things. We actually know one thing already. At the beginning of stage 2, our initial velocity is going to be the velocity from the end of stage 1. Stage 2 follows immediately on from stage 1. So we can write down straight away, this is 100 pi radians per second. That's what speed the motor's already rotating at when stage 2 starts. Omega-2, we're given in the question, is 4000 RPM. This is our final velocity of stage 2 in the of our whole motion. And again, we can convert this using the factor times 2 pi over 60 to get it into radians per second. Now, this time we don't have a nice round number, but putting it into your calculator, you do get an exact figure that you can use if you prefer to do so. So putting that in what we're going to get is 400 pi divided by 3. So while this isn't quite as nice as 100 pi, it is the exact value in radians per second. So if you prefer to work on that, you can do so. But we can also say, or this is the same as 418.879 radians per second. If that makes more sense to you, if they calculate it through, you can say that. And we're also told the value of alpha, and the angular acceleration in stage 2 is given to us. Alpha is equal to 40 radians per second squared, and those are the units we need to use for angular acceleration. So we have everything we need to do. And the question is going to ask us to do various things. First of all, in part A of the question, it wants us to find out the acceleration during stage 1, and that's great. So I'll just write this underneath stage 1. We're asked to find alpha. What is alpha and how can we find it? Well, if we look at our course notes, or we just know our list of equations of angular motion, we know there's exactly one formula that will have omega 1, omega 2, t, and alpha in it. And it's this formula here. Our final angular velocity is equal to our initial angular velocity plus the angular acceleration times time. So knowing the three pieces of information that we have already, omega 1, omega 2, and t, we can find alpha from this formula. Let's rearrange the formula to get it in terms of alpha. In doing so, we're going to find that alpha is equal to omega 2 minus omega 1 divided by t. And we can put in these values here. Now, it's really up to your preference what you want to put in for these values, where you want to use 100 pi for omega 2, or where you want to use a sensible rounded number like we've done up there. I'll put 100 pi in because I know it's going to give me a nice, more accurate answer on the calculator. I would say though, working to 3 decimal places, you're not going to get a significant level of inaccuracy. That would be absolutely acceptable in this question. Putting this on the calculator, 100 pi minus 0 is still going to be 100 pi. There's 100 pi divided by 6. And again, our calculator gives us a nice answer here of 50 pi divided by 3. But let's write this out for our final answer for part A in decimal form. And putting it into decimal form, we get an answer here of 52.360 to 3 decimal places, radians per second squared. And units are important because what we're being asked here is an angular acceleration. So we found out the angular acceleration in stage 1. And tick that off, that's all we need to do. In part B, we're asked to find the time required to complete the second stage of the motion. So again, we have 3 pieces of information and we want to find the fourth. And this time we have omega 1, omega 2, and alpha. And it's t we're trying to find. But you might spot this is the same 4 pieces of information. The only thing different here is the one that's missing. But that means we can use the same formula. So we go in our list of equations of angular motion, this same formula here is the formula that we would use to, just be careful there, a 2 again, and the same formula to find time, we can find acceleration. For this time, we'll make t the subject of the formula and work out what that is. So t will be equal to omega 2 minus omega 1 divided by alpha. And we have all the information that we need to find this out. Now, again, we can put in the exact numbers, or we can put in the decimal numbers. So we could do 418.879 minus 314.159, or we can just write in these exact numbers here, 400 pi over 3 minus 100 pi. You put this into your calculator and you'll get the correct answer. We're told that alpha is 40 in the question. Now, as I always say in class, you can work out these things separately. You can work at the top and then divide by the bottom. Or if you're confident with your calculator, you can put it all in. But this is the benefit of the tutorial problems. We can see whether we're getting things right or wrong and knowing how confident we can be with our working that goes into our calculator. Well, If we do this in 2 stages, our calculator will tell us, first of all, that on top of our fraction, we end up with 100 pi divided by 3. That's all still got to be divided by 40. And then we can divide that by 40. And our calculator, if we've been working with these exact numbers, will show us the answer 5/6 times pi. But that's not maybe a very useful way to think about time. So let us think about time in a decimal number of seconds. In decimal form, this is 2.6 seconds. So we can write that down like that. 2.6 seconds is the answer. And if you wanted to give an extra decimal place there, that would be fine as well. You would find that the answer we get, but probably should give it to at least 2. Is 2.62 seconds. So I've got 2.62 seconds here. And that's parts A and B satisfied. And so far, no sign of a velocity time diagram. That's going to come in part C, which we'll draw here. So let's see what we're going to have to do. Sketch both motions of the motor. So both motions mean stage 1 followed by stage 2 on the same velocity time diagram. And from this, calculate the number of revolutions. And I'll highlight that as another key word, because when we do this in rads per second, we're going to get an answer in radians first of all, so we need to convert this at the end, so we won't forget to do that. The number of revolutions the motor takes from rest to attain top speed. So that means from the start of stage 1 to the end of stage 2. And we're going to get a graph we've seen before, a triangle followed by another triangle that's sitting on top of a rectangle, but maybe just easier to draw what's going on here. The first things first, let's draw a pair of axes. We only need positive axes. We're going to have positive times and positive angular velocities. So we can draw in a y-axis to represent angular velocity, and we'll draw in an x-axis to represent time. This is a sketch, and what that means is this is not a scale graph. So we don't need to make sure every interval exactly measures 50 radians per second or 1 centimeter to 1 second in the time scale. What we're sketching in our points here, so our graph doesn't have to look perfect because we're going to get information from the points that we plot on it based on numbers we know from elsewhere in the question. So what we have on the y-axis, we have angular velocity. This will be in radians per second. And on the x-axis, we have time. That's in seconds. And what we're going to draw here is the journey that this motor is taking as it rotates. Well, what happens in stage 1? Stage 1 takes 6 seconds and starts from 0 radians per second. So our starting point is here. This is our starting point of our graph. At 0 time, we are moving at 0 angular velocity. After 6 seconds, we find that we're moving at 314.159. So let's, or 100 pi. We'll work with the decimal numbers this time just for a bit of variety to show you can do either. So when we get to the time of 6 seconds here, now make a wee mark, 6 seconds here, we're going to have this point here. And you can see that I'm not measuring any of these, I'm just going to be marking on my diagram what these are. And that's 314.159. I don't need to write the units because I've already indicated what the units are on the axes. So that's what happens after 6 seconds, and that's great. That's stage 1 complete. Everything that happens in the first stage is fine. Where we need to be careful now is what happens in stage 2. Well, we know in stage 2, we're going to rise to a final speed 418.879. So somewhere up here, we need to mark on this 418.879. And when does this happen? Well, it happens after 2.6 seconds, but let's be careful. It's 2.6 seconds after stage 1. So it's not here. It's not 2.6. That's not correct. It's 2.6 going this way after 6 seconds. So what that means is it's actually going to be 8.62 seconds because 6 plus 2.62 is 8.62. So that's where that comes from. So I can plot this point here as well. It's going to look a bit like that. Again, this doesn't have to be perfect because we're not basing this on a scale. We're not going to be reading anything off the graph. we're going to be using these numbers, which we have already, to calculate the area underneath the graph. So let's draw the graph in. I use solid lines, and I'm going to use in red, by the way. I'm doing mine in red just for illustration. I use solid lines to indicate the direction of the motor's velocity against time. And you'll see it's not the same gradient as the two stages. It probably looks slightly more pronounced if we did draw this to scale, but you can see there's two clear stages here, even from my rough diagram. And then underneath the graph, I'll use dotted lines to construct some triangles and a rectangle, which we're going to calculate the areas of. And the areas of these shapes is going to correspond. I've made this. So the great thing about sketching is I can adjust it afterwards to look correct. The areas are going to calculate to give us the angular displacement travelled in radians. I'll just tidy up a wee bit under my graph to actually say 8.62 is there. As I said, this is not an accurate scale, it's a sketch representing what's going on. So, and we have three areas, and we can label them. So we'll call this one area 1, this one's area 2, and this one's area 3. It doesn't matter what you call these, or the way in which you order them, or the way in which you calculate them. It's all about making sure we have the correct areas and we work them out each time. So let's work out these three areas. So area 1 is a triangle, and the triangle is equal to 1/2 times its base times its height. So the base of area 1 triangle, well, it's going from 0 to 6, so that base is 6. And if it's helpful, we can think about this by sketching these things. Well, there's no need to do this, but I'll do it here. The base is 6 for this triangle, so that is how I've got that value. And multiply this by the height. Well, the height of this triangle is the velocity at the end of stage 1. We can see that's where that triangle stops. So the height of this is 314.159. So let's write that in there, 314.159, or if you prefer to stick with the exact values, you could be using 100 times pi for that. It's the same. And the answer I get is 942.477. So great, that's area 1. Area 2 is a rectangle, and the area of a rectangle is its length times its breadth. So traditionally, the length of a rectangle is the longer side, and we know that already. The longer side of that rectangle, area 2, is marked there already, 314.159. That's great. But then we need to multiply this by the breadth. So the breadth is this side I'm drawing in here. It's the thin bit between 6 and 8.62. Now, we had to add a number to get that, so we know this is 2.62 as the breadth of the rectangle. So we multiply 314.159 by 2.62, and that gives us our second area. And this is a value of 823.097. I'm just keeping everything to 3 decimal places. We won't have our final answer this detailed, but it means that we're not losing anything through oversimplification and rounding. And finally, area 3 is a triangle, so it's 1/2 times its base times its height. We know the base of this triangle already. The base is the same as the breadth of the rectangle below. It's 2.62, so we can put that in there. And the height of the rectangle, well, let's be careful with what this is here, but it's a difference between the final and initial velocity from stage 2. This height is 418.879 minus 314.159. And you may have observed, we actually worked this out already. It was the same as 100 pi divided by 3. So whatever that is, we can put this in for our answer. And what 100 pi divided by 3 is 104.719. So we can put that in. So you can either calculate it directly by doing the subtraction here, or we could realize that we actually already know this value is 100 pi divided by 3. So since we're working with a decimal form, I'll put it in here. So 418.879 minus 314.159. And that gives us an answer of 104.72. So that's the height for our final shape under our graph. So we need to work this out so it's final later. So 1/2 times 2.62 times 104.72. And it gives us an answer of 137.183. And each of these areas represents something in radians. Before we start to talk about that, let's get our total area first of all. So our total area is equal to the total angular displacement of the motor through both stages. That's 942.477 plus 823.097 plus 137.183. And we get an answer of 1,902.757. And remember, this is in radians. And just write rad, not rad, so we don't confuse it with radians per second. Because if our y-axis is in radians per second and our x-axis is in seconds, it means anything we find underneath is going to be in radians. So we're nearly there. The question asked us to find the total number of revolutions. So total revolutions. And that's going to be equal to 1902.757. That's how many radians there are. And to find the number of revolutions, we divide by 2 pi, because there are 2 pi radians in every revolution. So if we go around a circle once, we've gone 2 pi, go around twice, we've gone 4 pi, 6 pi, and so on. So we need to divide this number by the number of radians in a single revolution, which is 2 pi, and that will give us our answer. And we get an answer of 302, and we can round it to 302.8 because we don't need to be overly precise here. This is our final answer. We've kept as much rounding as we needed to get to this point, 302.8 rev. And resist the temptation to write revs, because that again can be confused with revolutions per second. Depending on how you've rounded in this question, you might have a little bit of variation in your answer, but it should be here or hereabouts. And that's how we tackle a question like this. You'll see in the tutorial sheet, questions 5, 7, and 9 are all very similar to this. And it's also the sort of style of question that we can give you in the assessment for learning outcome 2.